So in question 10a, we're given the arithmetic sequence APQ, and we're asked to show that 2p minus q equals a. So since it's an arithmetic sequence, we can say that a plus p is given through this common difference, and p plus q is again given through this common difference. So we can also therefore say that p minus a is the common difference, and q minus p is also the common difference. Since these two are same, we can say that p minus a is q minus p. If I add p on both sides, 2p minus a equals q. 2p minus a equals q. So then minusing q and adding a, we get that 2p minus q equals a, which is what we want. In part B, we're given a geometric sequence AST, and we're asked to show that s squared equals to AT. Now the method I'm going to use is similar to this one, except it's a geometric sequence. So we know that to get from a to r, we would have to multiply by, to get from a to s, we'd have to multiply by a common ratio s. To get from s to t, we would again multiply by that same common ratio. So therefore s over a equals r, and t over s equals r, since they're both the same. S over a is t over s. Cross multiplying, we get that s squared equals to ta, which is at, and that's what we want. In part C, we're given that the first term of both sequences, as we already know, is a. So APQ, AST for the arithmetic and geometric. And we're given that q equals t equals 1. So both of these are equal to 1. And we're asked to show that p is greater than a half. So from what we showed earlier, if q is 1, we can say that 2p minus 1 is a. So 2p minus 1 equals to a. And then t is also 1. So s squared equals a. S squared equals to a. We know 2p minus 1 equals a, s squared equals a, so we can say that s squared equals 2p minus 1. So I'll say s squared equals to 2p minus 1. Adding 1, dividing by 2, we get that p equals to 1 plus s squared all over 2. And the question says show that p is greater than a half. Since we know that the first term is a, and what was it? And q is 1, this is 1, and this is 1, we will know that we can say that s is going to be greater than 0. So since s is greater than 0, it implies that p must be greater than a half, which is what we wanted. In part D, we're asked to find the first 4 terms of the arithmetic sequence APQ and then the next term. And then in part 2, we're asked to find the first 4 sequences of the geometric series, so AST and then the next term. We're also given that now a is 9, we knew that s was greater than 0, and q equals t equals 1. So I can write this as 9p1, and we know that p minus 9 equals 1 minus d, and we remember from earlier that 2p minus q equals to a. So 2p minus, what is q? Q is 1 equals 9. So 2p equals 10, p equals 5. So if p equals 5, we get 9, 5, 1. Then the next term, the common difference is clearly minus 4, so the next term will be 1 minus 4, which is minus 3. Now for part 2, we have 9, s, 1, and we know that s squared equals to at, so s squared equals to 9 times 1, 9, so s equals to plus or minus 3. But we can reject that s equals to minus 3 because we're going from 9, which is a positive number, to something, to another positive number. So therefore the ratio that we're dividing by must also be positive, so we can reject minus 3. So s is only 3, and we can see that we're going from 9, 3, 1, 9, 3, 1. We're dividing by 3 here, we're dividing by 3 here, so we're going to divide it once again to give us 1 over 3. So these are the first 4 terms of the geometric and first 4 terms of the arithmetic. In part E, we're given that our old arithmetic sequence and our old geometric sequence are formed to make a new arithmetic sequence, UN. We're given that the first term U1 is 9 plus ln 9, second term U2 is 5 plus ln 3, and so on. And we're asked to find the common difference in terms of ln of 3. So once again, we can say that U2 minus U1 is the common difference. So then we can say that 5 plus ln 3 minus 9 plus ln 9 equals to D. 5 minus 9 is minus 4. Ln 3 minus ln 9 is ln 3 over ln 9, which is ln of 3 over 9, which is ln of 1 over 3, plus ln of 1 over 3. This can be written as ln of 3 to the minus 1, and then that minus 1 is going to be taken down here by the log laws. So this is equal to D. So you can say that D equals to minus 4 minus ln of 3. In part 2, we're asked to show that the sum from I equals 1 to 10 of u sub I equals minus 90 minus 25 ln 3. So this is just basically saying we want to show that u1 plus u2 plus u3 all the way till u10 is equal to this. So the way I do that is I use my sum of an arithmetic sequence formula, which says that Sn equals to n over 2 multiplied by 2u1 plus n minus 1 times d. So by that, we can say that we want the sum from 1 to 10, so we want S10. So n is 10, 10 over 2 is 5, multiplied by 2 times 9 plus 2 ln 3, because ln 3 is, 2 ln 3 is ln of 3 squared, which is ln 9, plus 9 times d, which is minus 4 minus ln 3, minus 4 minus ln 3. This is 5 times 18 plus 4 ln 3, 5 times 18 plus 4 ln 3, minus 36 minus 9 ln 3, minus 36 minus 9 ln 3, 18, sorry, not 38, that's equal to 5 times 18 minus 36 is minus 18, 4 ln 3, minus 9 ln 3 is minus 5 ln 3, multiplying by 5, we get minus 90 minus 25 ln 3, which exactly matches this. So that is required. That is what we wanted.